Alright, so we have come to part 2 of the graphs, and what are we going to learn here? We learned a little bit about graph terminology in the previous part. We're going to learn about some special types of graphs in this part, and some of the terminology that is going to go with that. Right? And in the next part, we're going to learn about how to represent graph in the form of matrices and what is meant by graph isomorphism. We're going to learn about that in the third part, and we are not going to cover connectivity in the class. All right, so graph terminology and some special types of graphs. So we're going to learn about some basic terminology. We learn about some basic types of graphs, what is meant by a bipartite graph, and at the application of bipartite graph, which is going to be graph matching. And then we are also going to cover some applications there and how to get new graphs from some of the old graphs. Okay, so let's start with some definitions to learn about some basic terminology. So the first one, what does it say? So if you have two vertices in an undirected graph G, they are said to be adjacent to one another or neighbors of one another if there is an edge that goes from U to V or from V to U. All right, so this is an undirected graph, so just a line or a connectivity between U and V tells that there is an edge between U and V. It does not matter whether it's going from U to V or V to U. It's when it's undirected, it's basically considered to be both bidirectional. All right. So, and then you say that this edge is incident on the vertex U and incident on the vertex V. So that's the important thing to learn here. That means you have to say that the edge E that is connecting U and V is said to be incident with U and V. All right. So what's the second definition here? So when you have a graph, you have a set of vertices that come with the graph, right? So if you pick, let's say, one vertex, V, right? So the set of all the vertices that V is connected to is called the neighborhood of V. Right? So the set of all the vertices that a given vertex is connected to is called the neighborhood of V. Right? And your A is basically a subset of V. All right. So we denote n of A as the neighborhood of A. That is, all the vertices that are connected to all the vertices which are in the set A. Okay. Now, another way of saying this is neighborhood of the set of vertices A is nothing but a union of the neighborhood of each of the vertices which are in the set A. All right, so the next definition here. What is the degree of a vertex? This is something very, very important, right? So a degree of a vertex in an undirected graph. So we look at degree in a directed graph and all of these terminologies in a directed graph in a little bit, but here we are considering it in an undirected graph. So the degree of a vertex is basically the number of edges that are connected to that vertex is called the degree of a vertex, right? So the number of edges which are incident upon that vertex is the right terminology to use. All right. So the number of edges which are coming out or going into a given vertex, because this is an undirected graph, is called the degree of that given vertex. Okay. So let's move on. All right, so here is an example that tells you how to use the terminology that we learned in the previous slide. So here you're given two graphs, G and H. So that is graph G and that is graph H. Okay, and you have been asked to find the degrees and neighborhoods of the vertices of each of these graphs, right? So let's start with graph G. Right, so you're going to find the degree of each of the vertices. So let's start with A, right? So how many edges are connected to A? You have 2 edges here, right? So the degree of A is 2. So what about B? So how many edges are connected to B? You have 1 here, all right? You have 2, and you have 3, and you have 4, right? So you have 4 edges that are connected to B, right? So the degree of B is going to be 4. The same way, the degree of C is going to be 4. So there are 1, 2, 3, and 4 edges connected to C. Degree of F is also 4. There are 4 edges connected to F, right? Degree of D is going to be, the degree of D is going to be 1. There is just a single edge connected to D. Now, an important thing to notice here is G is a vertex in the graph, but it is not connected to the rest of the graph, right? So the degree of G is going to be 0 in this case, right? So the next part of the question is to find the neighborhood of the vertices of each of the graphs. So here is where you're finding the neighborhood. So basically the neighborhood of A is all the vertices that A is connected to. A is connected to B and F, so the neighborhood of A is going to be B and F. All right, so the neighborhood of B is going to be all the vertices that B is connected to, which is going to be A, C, E, and F. Okay, and so on and so forth. And let's come back to neighborhood of G here. All right, so the neighborhood of G is going to be the empty set. Okay, because there are no vertices that G is connected to. Right, so G is said to be disconnected to the graph, which we're going to learn about later on. But for now, G is a part of the graph, but it is disconnected from the graph. It's not connected to any of the vertices in the graph. And so the neighborhood of J is going to be empty, and the degree of G is going to be 0. All right, in a similar way, you can actually find the degree of each of the vertices in the graph H. Right, so degree of A is how many edges are connected to A. So you have 1, 2, 3, and 4. Right, now important thing to notice here is let's look at B. Okay, so how many edges are connected to B? So this is an undirected graph, right? So in an undirected graph, if you have a loop, right, so it's going to add 2 to the degree of that vertex, right? So you have edges AB, EB, DB, CB, and then also from B to B. Okay, so each of these edges connecting B to these other vertices adds a 1, but the loop adds a 2 to the degree. Okay, so you have 1, 2, 3, 4, 5, and 6. So the degree of B is going to be 6. All right, now and once again you can find the neighborhood of each of the vertices. So let's look at the neighborhood of B, right? So neighborhood of B is going to be all the vertices that B is connected to, and if you notice, B itself is also in the list. Okay, because there is a loop connecting from B to itself, you also have B within the list of neighborhood of B. All right, so now that we understand the degree of a vertex in in a undirected graph scenario, so this is a very important theorem, and it is called the handshaking theorem. All right, so what does it say? If you have a graph, right, which contains a set of vertices V and a set of edges E, and it's an undirected graph, then uh, if you add up the degree of all of the vertices in the graph, it's going to be 2 times the number of edges in the graph. Right, so the proof is very simple and straightforward. Right, we know that each edge basically is going to contribute twice uh, one for each end that it is connected to, each end vertex that it's connected to, right? And therefore both the left hand side and the right hand side of the equation are going to be equal. All right, it's going to be equal to twice the number of edges. So if you take an edge in the graph, it's going to contribute one to these one end vertex and once to the other end vertex. All right, so it contributes to the degree of two different vertices every single time, and therefore the number of edges, if you take in a graph and multiply it by 2, that's going to give you the sum of the degrees of all the vertices within the given graph. Okay. So now let's take a look at how this handshaking theorem can be used in order to solve some problems, right? So we have an example here. So how many edges are there in a graph with 10 vertices of degree 6, right? So according to the basically the handshaking theorem, we know that 2 times the number of edges is equal to the sum of degrees, right? Your sum of the degrees of all the vertices. Okay, so now we know that what is given here, it's given that there are 10 vertices of degree 6, right? So if you basically um, uh, try to find what is the total degree of the graph, that's going to be 10 times 6. Right, the degree of all the vertices in the graph is going to be 10 times 6, because one vertex has degree 6. All the 10 vertices are going to have 6 times 60. That's going to be the degree of all the vertices in the graph. Now this should be equal to 2 times m, which is where m is the number of edges in the graph. All right, so this basically tells us that the number of edges in the graph should be 30. Okay, so this is a problem we have solved using the handshaking theorem. All right, so let's look at another kind of problem that you can see. So if you have a graph with 5 vertices, is it possible that each vertex has a degree 3? All right, so now let's take a look at it. If we have 5 vertices and each with degree 3, if one vertex has a degree 3, 5 vertices are going to have 5 times 3, that is going to be 15. All right, so this has to be equal to 2 times m. All right, 2 times m, which is where m is the total number of edges in your graph. All right, so what does this tell us? If it's 2 times m, then this has to be an even number. Okay, but what do you have here? You have the sum of the degrees is basically an odd number, right? 3 times 5, it's an odd number. So if we try to equate that to 2, you're going to end up with your m is equal to what? 7.5. Is it possible to have 7.5? Is it possible to have 7.5 edges in a graph? No, right? So that is why you say that there cannot be 5 vertices which where each of them has a degree 3. All right, so this problem would actually take us to the next theorem that we are going to look at very shortly. So let's take a look at the second theorem in graphs here. So what does it say? It says that if you have an undirected graph, then you can only have an even number of vertices of odd degree. All right, so you can only have even number of such vertices which have an odd degree. So let's see how to go ahead and prove that. Okay, so Let's take a look at an example here to understand what is meant by this. So let's say you have a graph, right? So that looks something like that, all right? Um, okay, so let's say that is A, that is B, C, um, C, and then a D. All right. So what do you see here? So the degree of A is 2. The degree of B is 3. Degree of C is equal to 3. And the degree of D is equal to 2. Okay. So what do you see here? A and D are two vertices that have even degree, and you have your B and C, which are two vertices that have odd degree. Okay, so if you notice carefully, there are two vertices which have an odd degree. Okay, so that is what we are going to show in this theorem, that any graph that you take, there can be only even number of vertices that have an odd degree. Okay, so this is true for any generic graph, is what we are trying to prove. All right, so in order to prove this, let's say V is the set of all the vertices. Okay, capital V is all vertices. All vertices. Okay, now let's split it up into V1 and V2. Right, so let's split up the set V into V1 and V2. Right, and how do we define V1? V1 is all the vertices that have an even degree. So if you look at the example, so V1 should be A and D. Okay, the set of vertices A and D. Now V2 is the vertices, set of vertices which have odd degree. Okay, so in the example, if we look, B and C are going to be in the set V2 because they have odd degree. Okay, now you are going to assume, let's assume that there are m number of edges in your graph. Okay, so using the handshaking theorem, we know the first part, okay, which tells that 2 times m is equal to the sum of the degree of all the vertices. Okay, sum of degree of all the vertices in your graph. Now let's take this and basically divide it up into two different categories. Okay, that is the sum of degrees of sum of degrees of vertices with even degree, and sum of degrees of vertices with an odd degree. Okay, so this part is basically sum of the degrees of all the vertices with an even degree. All right, and this is basically sum of degrees of all the vertices with an odd degree. Okay, so now let's come back. So here you have all the degrees are going to be even. Okay, so if you add up a whole bunch of even numbers, what are you going to end up with? You're always going to have an even number. So the first part of this equation is always going to be an even number because you're adding up even degrees, right? Even degrees. So it's going to be an even number. So we know that the left-hand side of the equation, 2 times m, is also an even number. So any number you multiply with 2 is an even number. And we know that this part is also an even number. So what do we know here? We know that 2m, if you try to take it to the other side, minus basically sum of every edge from your set V1, the sum of degrees of everything in set V1. This part is going to be even. All right. So if this is going to be even, then now the right hand side of the equation contains only that. All right. So the right hand of the equation contains only that, and the left hand side should be equal to right hand side. So this should also be even. This should also be even. Right? However, what kind of degrees are we adding up here? We are adding up all the odd degrees, right? However, we know one thing. If we add two odd numbers, we get back an even number, right? So there has to be pairs of these odd numbers to add up, okay, in order to get this entire thing as an even number, all right? Which tells us that there has to be an even number of vertices with an odd degree. All right. So if we were to have odd number of vertices with an odd degree, then basically when you sum them up, you are going to be ending up with an odd number. But if you have an even number of vertices with an odd degree, adding two at a time, all right, two of these odd numbers at a time would give you an even number. And summing all of those even numbers up is going to give you an even number. Okay, so if you have any questions about this theorem, you can actually come by during office hours or ask me during the class, and I can go over this one more time. Okay. All right, so now let's move on and look at some of the definitions concerning the directed graphs. All right, so in a directed graph, right, um, basically it consists of a set of vertices and a set of edges once again. All right, and these edges have a direction associated with them, right? So they're called directed edges or arcs, right? And they are going from one edge, from one vertex towards another vertex, right? So the edges here are not just any tuples, they are ordered pairs, right? So they are ordered tuples, okay? So if you say there is an edge called u comma v, it's different from an edge v comma u, right? When you say there is an edge u comma v, that means the edge is starting at the vertex u and going towards the vertex v, right? Now, what is adjacency when it comes to directed graph, right? So if let's say u comma v is an edge in a graph G, then u is called the initial vertex and v is called the terminal vertex, and you say that the adjacent that the initial vertex is adjacent to the terminal vertex. All right. So you say that the initial vertex is said to be adjacent to V, and basically you say it's adjacent from U. All right. It's adjacent from U to V is what the terminology that you use. Right, but when it comes to loops, right, if there is a loop from a given vertex to itself, then the initial and the terminal vertices are going to be the same, right, for that edge, and the edge that is incident to and the vertex that it is incident from and the vertex to which it is incident to are the same. All right, so now let's take a look at the degree of vertices with respect to a directed graph, right? So since there is a direction corresponding to every edge in the graph, right? So the degree is basically split up into two parts, right? There is something called an in degree and there is something called an out degree. Okay, so like the name suggests, in degree is usually represented using degree with a negative postscript, and out degree is basically written with a positive sign in the postscript. Right? So the in degree is basically nothing but the number of edges that are coming into the vertex V, and the out degree of a vertex V is nothing but the number of edges that are going from going out of the vertex V. All right, so let's look at an example here. So we have an example graph G. So every vertex is going to have an in degree and an out degree associated with it, right? So let's take the example of your vertex A. Okay, so in your vertex A, let's look at how many edges are coming into A. Okay, that's going to give us the in degree of A. So you have a loop going out from A and coming into A. So if there is an edge coming into A, you count 1 there. Then you have an edge coming into A from E, right? You have an edge, that is all. So you have 1 in degree coming from the loop and 1 in degree coming from the vertex E. So the in degree of A is going to be 2. So let's count the out degree of A, right? That is how many edges are going out of A. So once again, you're going to count the loop, right? Because that is an edge that is going out of A. Then you have one edge going from A to C. You have an edge going from A to B, and you also have an edge going from A to E. So you have 3 plus 1, 4. So you have 4 as the out degree of A. So the in degree of A is 2 and the out degree of A is 4. So let's take another vertex. Let's take D. All right. So let's take the vertex D. So how many edges are coming into D? So you have an edge coming in from E, you have an edge coming in from B, and that is all. So the in degree of D is going to be 2. So let's see how many edges are going out of D. All right. So there's an edge going out from D to E. There's an edge going from D towards C. All right. So there are only 2 edges going out of D. So the out degree of the vertex D is 2. Right? So I want you to carefully look at the in degrees and out degrees of the other vertices that have been calculated here, right? And try and understand how to get the in degree and out degree of each vertex in a given graph. Okay, so here is another theorem. We're not going to cover the proof of this theorem, right? So basically this just tells us that the number of edges in a directed graph is equal to the sum of the in degrees of all the vertices, which is also equal to the sum of the out degrees of all the vertices in the graph, right? So simply put, the number of edges is equal to the sum of in degrees in the graph or the sum of out degrees in a given graph. All right, now let's move on and look at what are some different types of graphs, right, that are out there. So the first kind of graph you're going to look at is called a complete graph. All right, so like the name suggests, right, so it's a completely connected graph, which tells us that every vertex in the graph should be connected to every other vertex in the graph. All right, so we have several examples here. All right, and we basically denote the complete graph using the letter K sub n, where n is the number of vertices in the graph. All right, so the first example here is K1. All right, is K1. Basically that means a complete graph with just one vertex, right? Since it's just one vertex, you don't have to have an edge connecting to itself. All right, now let's look at K2, which is a complete graph with two vertices, right? So there has to be an edge from a given vertex to every other vertex, right? So there's only one other vertex, so there will be one edge in this graph. Now let's look at K3. So K3 means 3 tells us there are 3 vertices in the graph, and there has to be an edge from one vertex to every other vertex in the graph. So each vertex connects to the other 2 vertices. That gives us a triangle graph. So here you have K4, K5, and K6 with 4, 5, and 6 vertices respectively, and you can see that there is an edge connecting each vertex to every other vertex in these graphs. So this kind of a graph is called a complete graph or a completely connected graph, and it's denoted by the letter K sub n, where n represents the number of vertices in that graph. All right. So now let's take a look at some other kinds of graphs. The first kind is called a cycle, and the second one is called a wheel. So let's look at a cycle first. Okay, so the cycle is a graph that is represented with the letter capital C sub n, where n once again represents the total number of vertices in your graph. And in here you have a special condition that means that says that n should be greater than or equal to 3. You cannot have a cycle with the number of vertices less than 3. Okay, so here we have examples of C3, which is the smallest cycle possible. So you have 3 vertices, V1, V2, V3. And what is the special property of a cycle? So if you have vertices V1, V2, so on till Vn, then there has to be an edge between 2 of these adjacently listed vertices. All right, every 2 of the adjacently listed vertices. So from V1 to V2, V2 to V3, Vn minus to Vn, and finally from the last vertex to the very first vertex, Vn to V1 as well. Okay, so here we have 3 vertices, V1, V2, V3 in a cycle. So you have an edge from V1 to V2, V2 to V3, and then V3 back to V1. So here is an example of a cycle with 4 vertices. Here is an example with 5 vertices and 6 vertices respectively. Right? Now, the next kind of graph is called a wheel. Right? And it is represented using the letter W sub n. Right? So it's represented using W sub n. So what is meant by a wheel, right? So wheel is basically an extension of a cycle. So if you take a cycle with n, with basically n vertices, add an extra vertex and add edges connecting this extra vertex to every other vertex in your graph, then it is called a wheel. All right. So here is an example of a wheel with 3 plus 1 vertices, right? And that plus 1 vertex is the one in the middle, which connects with an edge to every other vertex in your graph. So here is W4, which contains 4 plus 1, right? The plus 1 is in the middle, connecting to every other vertex with an edge. So here is a wheel with 5 plus 1, and here is a wheel with 6 plus 1 vertices. All right. So remember one thing though, in a wheel, the total number of vertices is not represented by n. Okay, the n here represents the total number of vertices minus 1. Okay, it represents the total number of vertices minus 1. So once again, we looked at a completely connected graph, which is represented with a letter K, capital K sub n, where n represents the total number of vertices in the graph, right? And every vertex in the graph should be connected to every other vertex in your graph. Then we looked at cycle, which is represented with the letter capital C sub n, where n represents the number of vertices in your graph, and there has to be a vertex between every two adjacently listed vertices, and of course from the last vertex to the very first vertex listed. The next kind is called the wheel that we looked at. So this is an extension of your cycle. So basically a wheel sub n consists of a graph with n plus 1 vertices, right? It contains n plus 1 vertices, and out of which n of them form a cycle, and exactly one vertex connects to every other vertex using different edges. Okay, so after a complete graph, cycle, and a wheel, let's look at another special type of a graph, which is called an n-cube, all right, or an n-dimensional hypercube. Okay, so it's represented with a capital letter Q sub n, where basically the number of vertices in the graph is going to be 2 to the n. Right? So in here, n does not represent the number of vertices, but 2 to the n represents the total number of vertices in your hypercube. Okay, and how many bit strings can you have with basically n bits? You can have 2 to the n number of bit strings, right? So each of the vertices is represented using a bit string of length n. Okay, and there is going to be an edge between two vertices if the two vertices differ by a single bit. Okay, by a single bit position, then only you can have an edge between two vertices, and that is that special kind of a graph is called an n-cube. So here we have an example with n equals 1, and n equals 2, and n equals 3. Okay, so when your n equals 1, your 2 to the 1 is basically 2, so you have two vertices. When your n is equal to 2, your total number of vertices is going to be 2 to the 2, so that's going to be 4 vertices. And when n is equal to 3, you'll have 2 to the 3 vertices, that is going to be 8 vertices. Okay, so the very first one is your Q1, okay, and since your n is equal to 1, so your bit strings are going to be of length 1. How many such bit strings can you have? You can only have 2 such bit strings. One is going to be 0, the other one is going to be 1, right? And since these two differ by a single bit, there is going to be an edge between the two vertices. Now let's look at the second hypercube with n equals 2. So how many bit strings can you have with length 2? It's going to be 2 to the 2, which is going to be 4. And each of the bit strings are 0, 0, 0, 1, 1, 0, and 1, 1. However, you can only have an edge between two vertices which differ by a single bit. So if you notice, 0, 0 and 0, 1 differs by a single bit. The same way 0, 0 and 1, 0 differs by a single bit. So there will be an edge from 0, 0 to 0, 1, 0, 0 to 1, 0. A similar way, 1, 0 and 0, 1 differ from 1, 1 with a single bit, and so there will be an edge from 1, 0 and 0, 1 to 1, 1. However, if you notice, there is going to be no edge from 0, 0 to 1, 1 because both of those vertices differ by 2 bits. Okay? Alright, in a very similar way, how many bit strings can you have of which are of length 3? That's going to be 8. Okay? So that's going to be all the bit strings starting at 0, 0, 0 to 1, 1, 1. And basically there will be a vertex between there will be an edge between two vertices if they both differ by a single bit. So that's the example here. 0, 0, 0 differs from 0, 0, 1, 1 0 0 and 0 1 0. So there is going to be an edge from 0 0 0 to only these three vertices, and so on. So I want you to go ahead and check the third hypercube, Q3, and make sure that any two vertices that you pick differ by a single bit. Okay, so now if you were to take your n equals 4, then the total number of vertices would be 2 to the 4, that is going to be 16. Okay, they're going to be 16 bit strings of length 4, and you have to figure out all the bit strings which differ by a single bit and draw an edge between them to get a hypercube Q4. Right? So I want you to try and draw a hypercube of basically Q4, right? And try to practice it at home, right? All right, so other than the special types of graphs that we have seen so far, there are also other types of graphs which have been modeled particularly for, let's say, computer network architecture. And if you take up a course on computer networks later on, you're going to see these kind of graphs later on. So the first one is called a star topology here, and the second one is called a ring topology. All right, and the third one is basically a wheel-based topology that we have already looked at. Okay, so some networks use a star topology, for example, to represent a hub connecting a bunch of computers. You can have a ring topology to show a minimally connected network. All right, so a wheel topology basically combines the features of your star topology as well as your ring topology. Now, other than these three, you can also have something called basically an n-dimensional hypercube that we looked at in the previous slide, Qn, to represent basically a network that is useful in parallel programming, right? In order to basically show that which processors can work in parallel and which cannot, and basically to show how parallel processing progresses, you can use an n-dimensional hypercube. Okay, another common topology that is used is called a mesh network, which is used in, let's say, sensor networks and so on, where you have a single node or a vertex that is connected to a fixed number of other nodes, right? So which makes it look like kind of a mesh, as shown in the figure right here. Right, so this is a mesh network with 16 processors. Okay, now moving on, let's look at a special property which gives rise to another kind of graph called a bipartite graph. Right, so how do you define a bipartite graph? Okay, so let's look at the definition, focus on the definition, right? So if you have a graph, right, G, and if you can partition the total number of vertices in the graph into two sets, let's say V1 and V2, all right, in such a way that every edge that is present in your graph basically connects one of the vertices from your set V1 to another vertex from your set V2, then you say that the graph is bipartite. Okay, so you should be able to divide up your total vertices into two distinct sets, right? Such that every edge which is in your graph has to be between one, has to be connecting one of the edges from V1 to one of the edges in V2. All right, so here is an example of two graphs. One of them is bipartite, the other one is not. Okay, so let's take the example of your graph G here. Okay, it has vertices A through G. Okay, and there are edges connecting these vertices as shown, right? So let's take a look if you can divide all the vertices into two different sets, right? If you divide it such that A, B, and D are in one set, and C, E, F, and G are in another set. If you notice carefully, every edge in this graph is joining one of the edges from your first set V1 that contains A, B, or D to one of the vertices from the other set that contains G, F, E, or C, right? So G is said to be a bipartite graph. Now, if you take the example of H, you can see that you will not be able to divide it up into two such sets. All right. For example, if you were to put A, B, and let's say you have to put, um, if you were to put, let's say, B, F, and G, B, F, and D into one set. Okay, then you can notice here that there is an edge going from B to D as well. That means within the same set there is an edge, which there should not be. Okay, so you cannot basically split up the vertices in the graph H into two distinct sets such that the edges only exist from set V1 to set V2, and there should be no edges within the set V1, within the vertices in the set V1, or within the vertices in the set V2. Okay, so it's easy to show when a given set is bipartite, but in order to see that it is not bipartite, then we'll have to go through a couple of iterations to figure that out. Okay, so in fact what is shown in here is that you can basically divide it into a coloring problem. That is, you color some edges into with the same color where there is no vertex between the same colored vertices, whereas there is no edge between two same colored vertices. Okay, so let's look at an example here. Okay, show that C6 is a bipartite graph. So what is C6? C6 stands for a cycle with six vertices, right? So here is your C6, which contains a cycle with six vertices, right? So if you were to take the alternate vertices and place them in, let's say, set V1 and the other set of alternate vertices and put them in set V2, then yes, definitely you would actually have a bipartite graph. Okay, because there is no edge between the ones that I have marked in red, between the vertices that I have marked in red, so you can get a bipartite graph, right? Here is the division of vertices into sets V1 and V2, and if you notice, there is no edge between any two vertices in V1 or any two vertices in V2. Alright, so let's look at the other example here. Show that C3 is not bipartite. So here is your graph C3, that is a cycle that contains three vertices. Okay, so there is no possible way to divide these three vertices into two sets. Okay, because if we were to divide it as that and the other two in the other vertex set, then you have an edge between the two vertices in the other set, right? So there will not be a way to divide the cycle C3 up into two sets of vertices such that there exists an edge only between a vertex from V1 to V2. All right, so C3 is not a bipartite graph. All right, so let's take a look at a special kind of bipartite graph, which is going to be complete bipartite graph. All right, so once again, let's take a look at a bipartite graph. In a bipartite graph, you should be able to split up the vertices in the graph into two sets, V1 and V2, such that all the edges which are in your graph are between one vertex from V1 and one vertex from V2, and there should not be any edges between the vertices in V1 and between the vertices in V2. That is how you defined a bipartite graph, a regular bipartite. When do you say that a bipartite graph is complete? When you're able to split it up into two vertex sets, V1 and V2, such that every edge in V1, every vertex in V1 should have a connection to every other vertex in V2. That is when you say that a given graph is a complete bipartite graph. So how do you represent a complete bipartite graph? You represent it using the same letter K that you use to represent the a complete graph. However, there are two subliterals here, m comma n, where m represents the number of vertices in your set V1 and n represents the number of vertices in your set V2. So here we have four examples of complete bipartite graph. So the first one shows K2, 3. So your V1 set contains two vertices and your V3 set contains three vertices. And if you notice, there is an edge from every set in V1 to every set in every vertex in V1 to every vertex in V2 and vice versa. Right, so here is an example of K33. Your V1 contains three vertices, V2 contains three vertices. And this is an example of K35, and this is an example of K25 containing three vertices and five vertices respectively for K35, and containing two vertices and six vertices in K26 for V1 and V2 sets respectively. Okay, so now let's look at how to get some new graphs from the old graphs. So here we're going to learn about two definitions. The first one is a subgraph, all right, and the second one is a subgraph induced by a set. Okay, so what is meant by a subgraph, all right? So if you have a larger graph G with a set of vertices and a set of edges in it, okay, then you have another graph, let's say, containing the set of vertices W and the set of edges F in it, such that your W set of vertices is a subset of the vertices V, and your the set of edges in F is a subset of the edges in E. Then you say that your new graph H is basically a proper subset of is a proper subgraph of the graph G. All right, so in here we have basically been shown K5, that is your graph G, and basically this other graph that is shown here is a proper subgraph, of the graph K5 that is shown on the left. Okay, where you have a set of vertices in your proper subgraph, which is a proper subset of the of all the vertices from your graph G, and also the number of basically edges, right, is also a proper subset of the number of edges in K5. Okay, now what exactly is a subgraph induced by a subset W? So this is the second definition that we are going to focus on. All right, subgraph induced by a subset W. All right, so in here, so once again, this induced subgraph contains a set of vertices W and a set of edges F. All right, However, what is the special case here? The edge, an edge basically which is in your set F, all right, which is also in your set E, if and only if both the endpoints are in W. All right, so that means if both the vertices of which are connecting an edge are in the subgraph, then the edge connecting should also be in the subgraph. All right, so if let's say we selected A, B, C, and E are the vertices, right, that we selected to get the induced subgraph. Okay, then it should have all the edges between these selected vertices also present in the induced subgraph. So in here you see that there is there is also an edge from basically C to E, all right, from between C and E, which was not present in the previous example, right? So in short, if you have a subgraph induced, right, by a given set W, which is a subset of the number of vertices in the actual graph, then you should also have all the edges between these set of vertices which appear in the graph from the original graph from which the subset has been drawn. So why exactly are we studying bipartite graphs? All right. So bipartite graphs have several applications, and two of the applications are listed right here. The first one here is, let's say, job assignments, all right, or basically a marriage graph where you're connecting two different people. Right, so depending on the abilities of a person and the requirements of a job, you can actually do matchings between a given job position and the people available to do the job. All right, so in here you can basically use a bipartite graph along with a matching algorithm that is used in graphs for this purpose. Another example is marriages. So you can have a set of vertices with, let's say, men, or another set of vertices which is going to be all women, and depending on what the requirements are, right, you can actually connect the prospective people who can actually get married, who can actually date and get married, and so on. So these are two applications of bipartite graphs which are used along with graph matching algorithms. Okay, so now moving on, finally, how do you find the union of two simple graphs? So it's very similar to the union function that we did in sets, because essentially the graph is made up of two sets, right? A set of vertices and a set of edges. So you just basically combine the set of vertices together and combine the set of edges in both the graphs together to get the union of the two graphs. So let's say you have been given two graphs, G1 and G2. Then your union of the two graphs, G1 union G2, contains all of the vertices of G1 and G2 put together, along with all of the edges between different vertices in G1 and between vertices in G2 put together to form G1 union G2.